For those of you I don't know, my name is Kevin Lesht, and my talk today is titled Geolocation Explained. We get about 200 slides to get through with this talk here, so we're gonna have some fun. Just try not to blink. Okay. So the idea for this talk came from some work that we recently produced at Home Chef, where I work on our engineering team. Home Chef is a meal kit delivery company, and each week we put out a menu with meals. Customers can then order meals from a menu, and the ingredients for those meals come pre-portioned and ready to cook. We ship our orders out of 3 facilities scattered across the US. And until recently, all customers had access to the same set of meals regardless of where they were ordering from. But then we wanted to make a change. Our product team wanted to be able to offer additional meals to customers serviced by our West Coast facility. Much like a digital A/B test, we wanted to begin testing the impact of different meal offerings. Now, this opened up a number of different challenges that we had to work through, most of which revolved around figuring out what meals were eligible for a customer. If my order is being delivered out of our West Coast facility, I'll have access to all of the meals. But if my order is being delivered out of our Midwest or East Coast facility, I'm not going to have access to the test meals that are only available out of our West Coast facility. So for logged-in customers, this wasn't too bad to figure out. We've got the customer's delivery address, and we know which facility is going to be shipping an order for that address, so we can determine what meals the customer can access. But the logged-out experience became a little more interesting. For site visitors, we don't have any address information, and our marketing team wanted to be able to conditionally display the different menu offerings, and as best as we could, make sure that someone visiting the site from within the service range of our West Coast facility would see those test meals. Conversely, visitors outside of the range of our West Coast facility shouldn't see the test meals. So without access to the shipping address information that we have on logged-in customers, we had to figure out how to find the location for individuals visiting our site, and that's what my talk brings you today. We're going to step through how to geolocate site visitors and how to do it fast. Yeah. Okay, so to restate our problem, when someone visits our website, we want to find their geographic location and then conditionally display some content based on that location. And because we're dealing with display logic here, we really want to get to that location fast so we can bring our page content to the visitor as quickly as we can. So how do we do it? Well, we started by exploring a few options. First, we thought about leveraging some service with an API to handle everything for us. But this option got ruled out pretty quickly because it would add too much time onto our web requests. The amount of time it would take to send a request out to a third party and then hear back is just a non-starter. Next, we thought about Cloudflare. Cloudflare manages our DNS, and so a request coming to our site is first going to pass through them. They provide geolocation as a part of their analytics platform, so we explored if that information could be forwarded from Cloudflare to our app. Fortunately, they only offer country code, which just wasn't granular enough. Then we found this service called MaxMind. MaxMind provides geolocation data that allows you to find a location based on an IP address. And Rails does give us easy access to a visitor's connecting address. So this one seemed like it could be a good fit. The geolocation data comes as 2 tables. They separate the IP data and the location data. And the 2 are linked together by foreign key. A network block record belongs to a network location, and a network location may have many network blocks. Pretty cool. Only, let's take a closer look at this data, and specifically, this network address field. It looks like an IP address, but what's going on with this slash and the number after it? After some research, what we have here is CIDR notation. This stands for classless interdomain routing, which is a way to specify within an IP the number of bits that make up the networking portion of the address, and the range of IP addresses that are assignable off of that network. So how do we get the range of IP addresses from the notation? Well, let's start by breaking down what an IP address actually is. An IPv4 address is composed of 32 bits, broken down into 4 8-bit segments as divided by a period. Each segment is typically a numerical value from 0 to 255, and a segment can also be referred to as an octet to express that it's representing 8 bits of data. Plus, just a word that's more fun to say. So back to CIDR notation. The number following the / represents the number of bits that make up the networking portion of the address. Taking our example here, it'd be the first 3 octets that make up 24 bits and define our network address. The rest of the address can be used to define hosts on the network. So looking at this network address, any client on this network will have an IP address where that last segment is between 0 and 255. To put pictures to all of this, if we take a city like Chicago, there might be any number of internet service providers and any number of network nodes handling the clients of those providers. And each node is going to have its own unique network address and an allocation of IP addresses that can be issued off of that network address. And all of this can be represented by CIDR notation. Looking at network node 1, we know that the first 16 bits of the address are going to represent the networking portion. And so it's the last 16 bits that are addressable. For network node 2, we see 24 bits as the network address, so that leaves 8 bits as addressable. From this, we know that for a client connecting to network node 1, they're going to have an IP address that's within the bounds of that node's CIDR block. And just the same for network node 2, any client being serviced by this node is going to have an address that's within the bounds of its CIDR block. Once we know the bounds of a CIDR block, we can identify the starting address and ending address. And when a request comes in, we find the block record that contains our incoming address. From there, we just need to follow the foreign key to find the location. OK. So how do we code out that lookup? Well, we've got these 2 tables and say the IP address of the client visiting our site. The first thing that we could do is filter down our network blocks table to only those instances where the IP address fits between the starting and ending address. And with our network block records unique by starting address and ending address, that should take us down to 1 row. Once we've found that record, the next thing we could do is leverage that geoname ID field, which acts as a foreign key pointing to a record on the network locations table. What this means is that we can follow the value off of our network blocks table to join a network locations row where the geoname ID field is of the same value. Once we've joined our rows, we can set up our select to return everything off of the network locations table, since it's ultimately the location data that we care about. Bringing this into Rails, for you Active Record fans out there, here's what that syntax would look like. Nice and tidy, with the only change to our query that gets generated from this being that a limit is applied, which comes from the find by. But since we know that we should be finding a distinct match anyways, not a problem, and makes for a nice interface within our app. Putting everything together, we now have a system in place for taking an IP address and finding the location for that address. Pretty cool. So we send this work out the door, and everything's working, as expected. Only things are running a bit slow. Taking a look at New Relic, our performance monitoring service, around the time the work was sent out, the controller action where our query lives was already listed within the key transactions overview. If you're using New Relic, this list here is going to be where you'll find the longest running transactions within your app. Not a good place to be. And to give this a closer look, we can navigate through to get even more information about what all is happening. This chart is going to break down all of the components making up the response to the request. And if we scroll down a bit, we're given a nice breakdown table. Here, we can see that it's taking about 200 milliseconds to find our network location. And this 200 milliseconds is making up about 95% of our geolocation request time. Not the best for our end users out there, but this does offer up something nice. What we have here is an opportunity. Those performance reviews don't write themselves. So let's see if we can dig in and make some improvements. Let's go back to our query. Looking at things directly, we could make some assumptions, but we don't really have eyes into why this thing is taking up so much time. Luckily, database technologies provide us with some utility functions to detail out exactly how they plan to execute our queries. We'll be referencing Postgres as our database technology, but everything that we're going to talk through should generally apply for all SQL-backed databases. So back to those utility functions. By prefacing our query with an explain statement, Postgres will evaluate our ask and reference our schema and some statistics on our database, like table size, to plot out what it thinks will be the best way to respond to our query. The output here is a set of nodes that make up a plan. Each node represents an operation that Postgres will perform as a part of fulfilling the query. The main thing that Postgres is optimizing for when putting together a plan is speed. Postgres wants to return to you an answer as quickly as it can, and it's going to make some reasonably informed decisions about how to accomplish that. Now, taking things one step further, adding an analyze onto our explain statement is going to output what would actually happen when your query runs. Explain is projection, explain analyze is retrospection. The thing to be aware of with explain analyze is that Postgres is actually going to run your query and return both the plan of execution and also some data points on the actual run of each node in the plan tree. Here, we can see how long each node took to run and how many rows were evaluated at each step along the way. Now, explain statements used to look a little intimidating to me, and I think that came from just not knowing the language of all that was being said and also how all the pieces fit together. So this plan here jumped out as a really good candidate for demonstrating 3 fundamental database operations that we can step through and then leverage to understand why our query is running so slow and how we can make it run faster. The 3 operations that we're going to take a look at are going to be sequential scan, nested loop join, and index scan. Going to be the crowd favorite right there. I guarantee it. So a sequential scan can be thought of as a for loop. And to put this into terms of time complexity, because that's what our database cares about, a sequential scan is going to be a linear operation. What this means is that the time it takes to perform a sequential scan is going to be directly related to the size of your data set. In a worst-case scenario, where we start scanning at the top of our table and the item we're looking for is ordered last, the time it takes to get there is going to be the length of our data set. For that reason, linear operations can also be represented like O of n, where n is the number of items in your set. Now, if you're not familiar with this kind of big O notation, it's just a way of representing time in an abstract way. It lets us classify operations without having to deal with raw numbers of the data set or having to factor in variable stuff like computer processing power or language speed. It's a way to communicate a generalized runtime. So to put this into practical terms, taking our where statement from our geolocation query, we're looking for a record that can bound our IP address. And in order for Postgres to fulfill this condition by sequential scan, it's going to need to visit every item in our table to identify any matches. And that's what we see happening in our query here. This portion of the explain statement is telling us that Postgres visited a little over 1 million rows before it found a record meeting our condition. Now, something to note here, there are over 3 million rows in our network blocks table. And we know that network block records represent a unique range of IP addresses and that there should only be one record that can bound an IP address. But how was Postgres able to figure that out without having to visit all 3 million rows? Why was it able to stop filtering about 1/3 of the way through after only visiting 1 million rows out of the 3 million? Well, the answer is Postgres knows that this sequential scan is serving a higher purpose. Going into the execution of our query, it already has a plan and knows that part of that plan is limiting the return to one record. So once we've found a match, we can stop our scan and move on to the next step of the plan. Now, speaking of a higher purpose, Postgres has decided that the best way to perform our query is to get our network block data as a sub-step of our join statement. It's a good time to note that query plans are executed inside out, meaning that the far most nested nodes are going to evaluate before their ancestors. This step, being interior to the nested loop node, is acting as a dependency. Postgres has determined that to effectively perform our join, we're going to need the return from this step of the plan first. But with that in hand, let's now take a look at nested loops. Now, there are actually a bunch of algorithms that Postgres can choose from for joining two tables together, and nested loop is the most basic operation. What's pretty cool is that a nested loop join can actually be achieved by a number of different time complexities. The slowest version of this is going to be performed by sequentially scanning all of the items in your first table, and for each item in your first table, sequentially scanning each item in your second table. At each visit, we're evaluating the join condition for true to see if we found a match. May have gotten a little carried away with the slides here. We'll call it right about there. So in other terms, it's a nested for loop, which can be classified as multilinear time and can be represented by O of n times m, where n is the number of items in your first table, and m is the number of items in your second table. Now, this is a pretty slow time complexity. What's cool about understanding this, though, is that it highlights a reason why databases like Postgres always index primary keys. Usually, a join between two tables is going to be done by matching a foreign key that lines up with a primary key on another table. Coming off of our network blocks table, we already have a reference to the key we're looking for in our network locations table. And as we've seen, by running a sequential scan, we can step through each row to try and find a match. But an index scan offers us a way of getting there more quickly. So let's take a look at that. Now, Postgres supports a bunch of options for creating an index, and by default, it's going to use a balanced tree structure. So if we were to create a B-tree index on, say, a table's primary key, Postgres is going to gather up all of the values in that field and find a relative midpoint. It's then going to distribute our data downwards, following a simple set of rules. And these rules are going to be incredibly helpful if we want to read back our data. They are: a higher value will be placed to the right of the current node, and a lower value will be placed to the left of the current node. Following these rules, Postgres will step through our data set to build out our tree. Now, I do want to note, what we've built here is a bit of a simplification of a balanced tree structure and all that it can do, which is actually a lot more, like having more than two children off of a node, and even clustering data together on a single node. But I only had so much slide space here, and remember, we're already pushing like 200 slides. Let's see how we're doing, by the way. Okay. Back to indexing. What we're going to step through does highlight the fundamentals. It's really the rules for organization that we care about, and for the most part, those are the same. Following these rules, we're going to be able to traverse our tree and demonstrate that the time complexity of a B-tree index scan is logarithmic, which can be represented as O of log of n, where n is the number of items in our data set. So check this out. Take a value of 53. In order to find the node for this value in our tree, we can leverage the rules of the structure to answer some basic questions at each stop we make. Is the value I'm looking for greater than the current value? On our root node here, 53 is greater than 50, so we move to the right. 53 is less than 64, so we move to the left. And boom, we've found the node for our data point. By following this progression, we're able to throw away half of our remaining tree at each stop, And that's what makes this logarithmic. Following a sequential scan, we would have had to have visited each row on our table until we found a match. And the cost of that operation would scale linearly with the size of our data set. But with an index scan, we don't have to visit every record. For each move we make, we effectively filter out half of the remaining data. And that's how logarithmic operations really show their speed. Say we start kicking up the size of our data set. To find a record using a sequential scan, which is a linear operation, the time it would take to find an item is going to be directly proportional to the number of items in our set. But using an index scan running in logarithmic time, each doubling of our data here only introduces one added unit of time onto our search. We can find our way through 1 million items in at most 20 progressions through our index. With logarithmic time, our data can grow exponentially, and the cost of finding a node won't change all that much. It's super powerful. Now, one thing to keep in mind, indexes exist separate from your data. What this means is that once we've found a node matching our condition, Postgres is going to follow some metadata stored with that node to access our table row, which lives in what's called the heap. Not a lot we're going to dig into here, but it is a good thing to have an awareness for. Consider that for every table change, your database may have to update any indexes that might need to understand that change. The concern here could be that if you have a heavily indexed table, all of your write and delete operations might get expensive as you spend time keeping your indexes in check. Not something you run into often, but some good knowledge to keep in your back pocket for your next database trivia night. Okay. So now that we have a handle on indexing, let's look back at our query plan. We know that in order to fulfill our join statement, we're going to have to visit both tables. There's no getting around that. And luckily, we dodged the double sequential scan. Our network location's geoname ID index is allowing us to more quickly scan that table for any rows that match the foreign key on our network block rows. Now before, we set up a nested loop join as multilinear because we had to sequentially scan both tables. But knowing that we're able to leverage the index on network locations, the cost of our join is now going to come in at O of n times log of m time. One sequential scan to find network block records, and then for each record that we find, which from our limit will just be 1, an index lookup to find our network location. So if we were looking to optimize this query, it's that sequential scan that grabs our attention. This thing is really slowing us down. Taking a look at the actual runtime, that's everything right there. The visiting of over 1 million rows, it's killing us. So what if we could evaluate that table with an index scan? That would take us to the most performant option for our query here. O of log of n plus log of m time. One index lookup by IP address to find our network block record, and then using the geoname ID value off of that record, one index lookup to find its network location. By understanding the time complexities associated with each operation, we know where to look and can leverage this stuff to better design our query or our schema to take advantage. Now remember back to our explain statement. Postgres is going to provide you with what it thinks is the fastest query plan. And it's usually really good about making that decision. But Postgres only has available what we give it. And so in using explain statements, we might be able to identify an opportunity for adding a new index, or maybe we could change our query altogether to coerce Postgres towards putting together a better plan. And that's what we were able to do here. An index on the starting IP address and ending IP address was already available. But Postgres still decided to go for the sequential scan. It turns out that by throwing a limit statement onto our query of a low enough value, in our case 1, which came from active records find by, Postgres thinks that a sequential scan is going to find our record faster than going through the index. Remember, the query plan is built on projection. In actuality, though, we saw from the numbers that this assumption Postgres is making turns out to be the bottleneck of our query. So how do we influence Postgres towards using that index? Well, turns out to be pretty simple, clever, but simple. If we add an order statement to our query, Postgres knows that it's going to have to sort our rows at some point in time. And with a sequential scan, this has to be done as an added step. Only after we've collected all of the rows can Postgres figure out how they should be sorted. But if you remember back to the rules of how an index is designed, they're built around an order. Postgres is able to leverage this, and as it progresses through an index scan, it can keep track of how the rows it picked up were ordered. This allows us to sort along the way and eliminates the need of that extra step that came with the sequential scan. By adding an order statement to our query, Postgres is going to change its plan to favor our index so that it can reduce what would have been 2 steps, a sequential scan followed by a sort, down to 1 step, an index scan with sorting along the way. By engaging our index, we lose the sequential scan and pick up a huge performance win. With the initial version of our query using the sequential scan, we had to filter through about 1/3 of the network blocks table, and that led to a runtime of about 200 milliseconds. Now, with the index scan, the runtime on this thing comes down to 0.05 milliseconds. Look at that change. Rolling the updated query out to our app, check out this reduction of runtime. Before, a geolocation request took about 200 milliseconds and was one of the top offending transactions in our app. Now, doesn't even register. 1.67 milliseconds. That's over 100 times faster right there, and that is going to look very nice on my performance review. And I hope it made for a nice talk, too. Thank you. Yeah. Thank you all for attending. Thank you to our organizers, and thank you to our sponsors. The slides for this talk can be found at kevinlesht.com/RailsConf 2022. If you have any questions or compliments for me, you can find me on Twitter at kevinlesht. And if you'd like to check out my other projects, you can keep up with those at kevinlesht.com. Thank you.